Alright, hell yeah. This is part 3. This is dynamics. We have this problem, and we're going to blow it up real big. And that'll help us with the geometry, because what we're going to do is use geometry to get the answer instead of differentiation. What it asks is that it says, hey, this thing spins, and then this actuator moves down. We've seen it quite a bit, because I've made a model of it. This is part 3. And alright, so they want to know when this thing's at a 60-degree angle, what's the velocity? And we just need to know, like, hey, the definition of velocity is change in position. So we can say change in x, change in t generically. In this case, maybe this is the y direction. We want to say, hey, we want to know the change in y, change in t. And so, and then I'm just getting kind of better at it. It's just like, because sometimes I don't like the generic x and y, but we can call this distance y. So maybe that's kind of what we're shooting for when this is at an angle of 60. If we can measure that distance and then change this angle and then measure the distance again, we're going to know that change in position. And then we just need to know what time frame it took. Because this is spinning at a constant angular speed, that will probably be a little bit easier. Okay, so hell yeah. So this circle right here we're going to draw. So this is our pivot point of the circle. You know, the pivot point's not in the middle, but we do have a radius. So any measurements off the center will be the radius. So there's the radius right there. In this drawing we have eccentricity. So this is the distance from this pivot point to the center. That's going to be E. And cool. So this problem in this book, you know, is classic, where you have a triangle that's not a right triangle, but you can make a link the two triangles together at 90-degree angles, and now you can link. If I know this triangle, you can. If we know a few things, we know quite a bit about both these triangles. Okay, so for this problem, and if we do differentiate, they want everything in terms of this angle right here, because this is the angle theta that we're going to measure. You know what I mean? We could move this disc, and then we could be like, okay, hell yeah, it's at a 60-degree angle, and so all our measurements have to come from this point. So this video is just kind of like not going over the trials and errors. Well, hopefully we get to that in other parts of this problem. But this video is just about, hey, just going for the answers. So how do you do this? Well, let's go kind of back to the basics. If I know a hypotenuse, hell yeah, and I know an angle, well, I just need to know like an angle and then one other thing, and then I know everything else about the triangle. So just in this case, it just happens that I know the hypotenuse. So if I know the hypotenuse and I know the angle, I know both these sides. I can do, hey, if this is the angle, the sun is shining on the sinin, and so it's going to be the hypotenuse, the larger number, times the sine of the angle, and this is going to be a percentage. Sines and cosines are percentages of the hypotenuse. And so the same thing's true for E cosine theta. Whoops. What would this mean? It means that we take the hypotenuse, multiply it, that larger number, the hypotenuse, by a percentage, and that's going to be the percentage of the, it's going to be this length, but a percentage of it is going to be in that direction. Okay, sweet. So we know this length, and then we don't want to lose, forest for the trees. What we're trying to find is this whole length. We're going to call it y. You know what I mean? So this is same thing here. This is that dimension y. Y is going to be equal to, hey, this segment plus this segment. And this is kind of the tricky thing, is like, hey, maybe you would do the same thing here. You would say, hey, I know this radius and I know this angle. I'm just going to call it phi. Typically in some books you just call it theta 2, this would be theta 1. But we're just going to call it phi just so it's totally different. So I can do the same thing. I can say the hypotenuse, sine of phi. Well, what's that going to be? That's going to be this. Hypotenuse, sorry, it's going to be the radius and then sine phi. That means that this is going to be the radius cosine phi. Okay, cool. You know, I mean, you can go down that road, but what this problem wants to know is like, hey, I want to input 60 degrees right here and find this length. If I input 60, okay, I know this because I know my eccentricity is 60 millimeters. I know my radius is 100 millimeters. Those two things are given. And I know my angle is going to be 60. So I do know this length, but I don't know what phi is. So maybe you would just do an equation to relate phi and theta, and let's set that up, you know, because it couldn't be that hard. We do know that this length is going to be the same on both of these. So we can see that r sine phi is equal to E sine theta. And then you just start solving for phi in terms of theta. So you bring the r downstairs and get rid of it right there. And then you take the inverse sine of this. And then that's going to be theta. Okay, hell yeah. But it's just a little bit ugly, you know what I mean? Inverse sine of a ratio times sine theta. So why not do the pro move and you know what I mean? So let's just cross these out like that. We didn't even go down that route. And so we're just sitting with we know that this is the radius, but we do know this side in terms of theta. This side is this side of the triangle, so we can also say that this is E sine theta. You know, so we know this hypotenuse, we know this side. So now how do we get this side? We use Pythagorean's theorem. This squared plus this squared equals this squared. But we don't know this, so you kind of have to use Pythagorean's theorem kind of in reverse. So Pythagorean's theorem's a squared plus b squared. Everyone knows it. Okay, but let's say you want to solve for this angle B. Like we know A, we know C, but we don't know B. So we're going to say B squared is equal to C squared minus A squared. And then you'd say B is equal to C squared minus A squared. And it's just really good to do this as much as possible to get used to it. So you can be like, oh, I get it. It's the hypotenuse squared minus this side squared. And it makes sense because if I have both of these sides, I got to do this squared plus this squared, square root it to get the bigger number. But if I already know the bigger number, I know that this has to be smaller. So I'm taking the hypotenuse squared minus this side squared, square root it, and that's what we get. So we have the hypotenuse squared, r squared, minus this E sine theta squared, which is just E squared sine squared. I just kind of made it a little bit like that. And then we're taking the square root of it. Okay, so hell yeah. So now we know this length. We know why. If we throw in theta, we can throw in 60 degrees right there. We know what r is, we know what E is. We know everything about it now. So now at angle 60, we know what that dimension is in the y direction. Hell yeah. All right, so now comes the part of the problem is just like, well, how do we find, again, the velocity at 60? Well, we need to, I use the 3-point method. Let's find the position at 60 degrees. You know what I mean? So, like right here, if theta is 60, let's see what I did. I put square root of 100 millimeters, that's the radius. Squared minus 60 is the eccentricity, squared sine squared 60. Plus this 60 eccentricity cosine 60. Cool, and we get an answer. And so that answer for that one is going to be 115. You know, I was in radians, so just make sure this was when I was in radians in my calculator. Changed it to angle. Or whatever the hell they call it. Yeah, anyway. So so this is going to be 115.44 millimeters. And again, like, hey, this is 100. And then when this is swept out to 60, this thing is going to be more than the radius. It's going to be about the radius away. So it's always good to give yourself a visual. It's like, okay, if this is at a 60-degree angle, this thing's hella low, but it's just right there. Okay, sweet. So so it's the 3-point method. So we need to take an and if all we're trying to do is find the velocity, you don't need to use 3 points, but we're going to find the acceleration too, and it's just good practice. So we're going to go back. we're not going to go to 59 degrees. We're actually we're going to know that we have this method down. So we're going to go 1,000th of a degree before, and so we're going to change angle theta to 59.999. Now, I wouldn't do this for your first go around. I would just change it to 59 degrees. Cool. And then when you throw in 59 in here, hell yeah, you're going to get a number, maybe like one, you're going to get a number that's a little bit taller, like 116. And then when you throw in 61 degrees, you're going to get a number that's going to be like 114. You know, but I didn't do that. What I wanted to do was get a hell of exact answer. So we throw in theta is 59.999, and then we throw in theta is 60.001. And we get these three positions. This is 115.44, you know, 0, 115.441, so it's going down, and then this is 115.43. Okay, sweet. So that's going to be the change in position. Again, velocity is change in position, so we're going to say change in y, change in t. So now we need to figure out what the change in time was in between 1,000th of a degree. And so we go over here. Our angular speed of this thing is 1,000 revolutions per minute. Just mentally, I like to change it to degrees per second for whatever reason. Well, two things. I want to go from revolutions to 1,000 revolutions per minute. 1 minute divided by 60 seconds. That's going to give me 16.6 revolutions per second. So that kind of gives me a visual. We're going to say that 360 degrees is 1 revolution. So we get 6,000 degrees per second. And we're just changing 1,000th of a degree. So we're going to take 1,000th of a degree divided by 6,000. Seconds pops upstairs. And yeah, this is why you want to take like a bigger bite. You know, at least like 1 degree, maybe even 5 degrees, 10 degrees, just to get an answer that's, you know, where you can see the changes visually. But since I already kind of know this process, I don't mind holding these tiny numbers in my calculator. So the change in time is 1.6. It's less than a millionth of a second. It's a 10 millionth of a second. All right, hell yeah. But anyway, and so we have that. So the change in position is just going to be, hey, this minus this. So if we take this minus this divided by this change in time, hell yeah, we get velocity. And so that's going to be the velocity right there. Negative 7.35 meters per second. And we're going to do the same thing. We're going to change this position from there to there. This minus this divided by that change in time. And so we have our velocity does change a little bit. The average between these is just adding them together, dividing by 2. And booyah, we got that average velocity. But because we have the velocity at 2 different points, we're also going to take the difference between those, this minus this, and then divide by that change in time. And then we see that, whoa, okay, so our acceleration, it's getting faster going downward. So it's like, hey, slowly going down, and then it's going faster in that downward direction. That's why the acceleration is also negative. And it's going to be 141 meters per second squared. Okay, hell yeah. Oh, and then the other thing about this, how do we compare that to something? You know what I mean? Because what is gravity? Gravity is 10 meters per second squared. So I'm glad I thought of this. Every time you get, especially when you're working with mechanical things, they can generate a lot of acceleration. Know that humans can't. If you put a human, if this was an amusement park ride and you put a human right there, they would die, because we're going to divide negative, or just 141 divided by 10, and this is 14, you know, basically just 14.1 Gs. You know, it's very easy to do the math, but you can't sustain more than 10 Gs for just a fraction of a second. You know, 10 Gs is lethal. Even 6 Gs for more than a few seconds can be pretty detrimental, if not lethal. So anyway, but and then just for further problems, it's this acceleration. The acceleration is what's going to cause the force. So if we go F equals ma, we rearrange this and say the force. Sorry. well, hell yeah. Yeah. We know the acceleration. We might know what mass, you know, hey, this has a mass and it's accelerating. So there must be a force on that mass to do so. Anyway, all right, booyah. So that was part 3 of using, all we did was trigonometry. All we did was just measure things, find their angle, and try to measure things and then change the angle and then measure things again. But that is the differential. That is the differentiating process. Finding a differential equation just does that for you. It says, hey, I'm just going to input the angle, and what's going to output, well, it is velocity. You know what I mean? So, but let's see. Yeah, hell yeah. And this was, hey, I input the angle, output is this position. So that was fairly easy. I think we can all see that in a, you know, in a 3-dimensional 2D plane. It's just like, yeah. But derivatives are tough because once these things are changing, to actually do the derivatives, there's a lot of places to go wrong. So that's what I'm hoping to explore in just a multiple part video. This was part 3. So thanks for joining me on this one, and guess what? That's a video.